I have some flexibility, so later on I can always gear things towards, more towards like the theory aspect, more towards the detectors that people use. If people have a preference, somewhere or the other. Or something people want to hear about, like some term that people have heard but are curious about what it means. What? Higgs boson. Okay, I think that would be good. Yeah. Okay. Yeah, so I'll actually talk a lot about the Higgs boson. That's kind of one of my main examples for some of the more theoretical aspects as far as how we're able to find where the Higgs boson is, essentially. I'll chat a little bit about why it's important. Anything else you want to hear about? Yeah. Neutrinos. Those are fun. Yeah, I'll chat about those too. Okay.
Do you know Chris Geyser?
What?
Do you know Chris Geyser?
Chris Geyser?
Yeah.
Is he,
He's my reading nerdy friend who spends a lot of time around here in Atlanta studying particle physics.
Oh, that's interesting. Yeah. I actually work on I have an office on this floor full of like particle physics people, but I don't know if I've seen Chris Geyser around there. But
He's a kid.
he's a kid, a little guy. Maybe did he show up to like seminars or stuff like that? Particle physics. People that are really curious about physics, every Monday, not during the school year, there's like an open sort of, I guess you call it like the colloquia or whatever, at the physics department. And they'll usually have some cool topic, they'll bring in occasionally bring in like Nobel Prize winners and stuff like that to give chats. And those are usually open to the public. So people learn about like the physics department webpage, they can see that stuff. I guess we can begin. So I'm Ben Horitz. I'm your lecturer here today. So today we're going to be talking about particle physics. So if people sort of are up on the history of physics to any extent, the general trend of physics over the past, few thousand years has essentially been a rush to smaller and smaller scales. Behind each level, we sort of like an onion, you sort of peel it back, and you see cool new things. Back in Plato's day, they sort of theorized maybe there's some aspect, something that they called an atom at the time, which is indivisible, the smallest little unit of matter. And we've been trying to sort of work slowly and keep on sort of thinking that we find it, but then there's something new pops up. So, we found, way back in the day, people sort of discovered molecules, they sort of looked at different chemicals, water, etc. And then we found, if we're able to apply really strong currents, we can turn water into hydrogen and oxygen, a whole new different things. And then we found out that, actually if we, shoot really high power electrons through those, we find that, there's actually some substructure inside. There's something small inside those atoms. So we find electrons, then we found the nucleus, then we found, if we smash two nucleuses together, we see cool things. So essentially what we've been doing is just slowly trying to pick apart everything, using higher and higher energies to get to the smaller and smaller things. So there's a fun little cartoon about this, which is, I'll let people look at it, but essentially, there's a reason why we're physicists, not biologists, because it'll get pretty gruesome around the bio labs if they let us too close. So what have we found so far? We've been working at this for thousands and thousands of years. What particles have we ended up finding? What are our building blocks? And there's a fun model that we created, which is called the Standard Model, which encompasses 99% of all physics that we see, essentially. And here are the building blocks of the Standard Model. I don't know, people have sort of heard about quarks and stuff like that before, but there are, inside the Standard Model, there are three fundamental forces. I don't know, do people name the three fundamental forces? The fourth is gravity, but that's tricky. But can anybody name one of them?
Electromagnetism.
Electromagnetism, yeah. The what?
Molecular force.
Oh yeah, weak force just generally. Weak atomic force, as they call it. Yeah.
Strong force.
And strong force, exactly, yeah. So we've been able to find the carriers of this force, the little particles that transmit this force. So the photon is in charge of the electromagnetic force. The gluon moderates the strong nuclear force, they call it. And the weak force, oh, I guess it says that there. But the Z boson and the W boson are what moderate these forces. And they're called bosons because there's this little property, kind of a weird property called spin, which is essentially a measure of how, if you have a really strong magnetic field, and you pass these particles through that field, how they'll react. Whether they go up or down, is sort of an aspect of spin. And then there's another aspect called charge, which people are probably familiar with. Essentially, if you have a strong electric current, how will it respond to that electric current? Mass, the way we measure mass is we can't take a little scale, right, and actually measure the particle directly. But what we do is we submit it to a force. And people remember our fun little physics formula, F equals ma. Essentially, if we can trap the particle, we apply a force. Usually what we do is we have lots of particles and we apply a strong electromagnetic force. And then we just see how fast it accelerates. And from that we can tell its mass. So we have our forces, then we also have our quarks. Quarks are the main building block of most of the matter that we see. It encompasses most of the mass. You can see these are sort of weird units, but particle physicists use something called electron volt to describe mass. And these are mega electron volts, so they're what is that, 1 million electron volts, something like that. And compared to these guys, which are on the order of around an electron volt. So much, much smaller these guys than these guys. And so these quarks build together to form protons, neutrons, and some other weird particles. And these guys, the neutrons are a little bit strange because they are very, very massless. In fact, for most of physics, since we discovered them, we sort of assumed that they were massless, but slowly we're starting to discover they have tiny, tiny bits of mass associated with them, which I can talk about a little bit later. And then there are electrons, which, as people are probably familiar with, circle the nucleus of the atom. So here's sort of a nice way. This is how physicists view these forces. They draw these things called Feynman diagrams. And we can sort of see how the electromagnetic force works. Let's say we have two electrons. They transmit what's called a virtual photon. We call it virtual because we can never actually detect this photon. We can't put a little detector between the two electrons and actually see it. Because if we actually see it, it won't end up transmitting a force. Because the way we sort of will detect it is by putting a detector there, right? And seeing the photon collide with it. But if it collides with the detector, then it won't interact with that other electron, so that we won't have the force overall. So it's called a virtual photon because we can never actually directly see it. Here we have the weak force. Now the weak force is very interesting. The weak force is what's responsible for most radioactive decays. If people have ever heard of, uranium being radioactive, emitting all these high power radiation, it's caused by the weak force. And the weak force can carry a charge with it, an electromagnetic charge. So it can do things, for example, turn a neutron into a proton, but they'll also emit lots of other crazy particles. So that'll be a really high-powered electron, and a very high-powered anti-electron neutrino. And then there's the strong interactions, which are moderated by our gluons here. And this is sort of a funny thing. There's sort of this bookkeeping involved when you're looking at interactions with a strong force. And physicists decide to use funny colors to describe the different quarks. So, and essentially, at the end, there has to be no color in the interaction. So you have to have as much green coming in, as much blue coming in, as what comes out of the reaction. So here we see a reaction between two quarks, for example. This is the force that binds together the nucleus, and binds together the protons and the neutrons. And then we see also between neutrons, we have the same kind of force. This is called a pi meson. If we look to see what mesons are, we can see that quarks combine together to form various sorts of particles. People are probably familiar with the protons and neutrons. So here's our proton, here's our neutron. But they can also form together to make very strange particles. And we usually don't really care about these particles because they decay very quickly. They quickly turn into more normal matter, for example, neutrons and protons. Neutrons and protons are very stable, we say. They don't decay into other things. But, for example, you can also have, all these other sort of weird family, like lambda baryons, sigma baryons, and then there's also mesons. Mesons have only two quarks, while baryons have 3 quarks. So the mesons are even weirder, and usually these guys decay extremely quickly, on the order of nanoseconds or milliseconds. So we can never really directly detect them, but we can see what's their byproduct. We can see them going, we can see that they'll decay in some certain way, and we can detect the byproducts of the decay to sort of infer that they were once there. Are there any questions so far about these things?
What do those numbers stand for?
Oh, yes. So these numbers here, I think are the mass in electron volts, or maybe mega electron volts. And then there's also these numbers. These are the spin numbers, because the quarks have a spin, and when they combine together, they'll form different types of spins up and down. So these are the different spins associated with particles. And there's this cool sort of way to arrange them. And in fact, for any given few species of quarks, you can make a cool new chart to arrange. And these are called the Gell-Mann eightfold way. And you can form them for each different set of quarks to make a whole new little family of particles. And there's some sort of deep physics involved with how you can arrange them this way and what this really means. In fact, they were able to predict that these particles would occur. They first couldn't find, this particle, and they found everything else. But then, a smart theorist came around and said, I expect to find another particle here with some certain mass, and then they ran the experiments, and after a couple of years, they were able to find that particle with exactly that mass. So it's like one of these really high accuracy things they were able to sort of figure out pretty easily. Any other questions about stuff so far? Or just making some amount of sense? People sort of seen a bit of, at least this chart, have people seen this before? This kind of way of arranging particles? So let's go back to these Feynman diagrams. Feynman diagrams are sort of the core of particle physics. These are what theorists always use if you walk around some physics building. Some you'll probably see lots of these guys on the board. And essentially, they're almost like tinker toys. So you can combine them together in certain ways to get to sort of theorize reactions. So the most basic one for ENM is you have so here we have a photon coming out, and here we have some sort of electron. Essentially, any particle that carries charge coming in and coming out. Okay, so this is our basic building block. Now we can form these guys together to make cool new diagrams. So in that example, we have we just sort of tie this up together here. And we have, usually this is considered the time direction. Sometimes in some diagrams they might flip it around. They might have this be the time direction. So what we see here is we have an electron coming in, an electron coming in. Our virtual photon is exchanged, so they interact, and then an electron comes out, an electron comes out. So this is, the model you might think about. If you have two electrons sitting in space, and they come close together, they'll eventually be repelled away from each other, right? Because like charges repel. Meanwhile, let's change this around. Let's have an anti-electron. So in the same way that we have particles, we have antiparticles. And antiparticles will have all the same characteristics, the same mass, the same spin, except that they'll have opposite charge. And the way we represent antiparticles is with reversing this line. So we reverse the line, if I can erase well. And now we have an electron and a positron coming in. And like sort of it's drawn as though they repel each other. But in reality, they'll probably actually, if you sort of think of this as a spatial axis, they'll probably attract each other. So what's the interaction between an electron and a positron? Do people know what happens when you combine matter and antimatter? You ever heard about this? Yeah, I see people going, poof. Essentially there's a huge explosion. All of the energy of the electron and the positron will be converted to just gamma radiation, really powerful radiation. And gamma radiation is a type of photon. So let's draw a different diagram for what an electron and a positron annihilating. Annihilating is sort of the term they use to describe these kinds of poof reactions, right? So here we have our two little tinker toys, and we can combine them together. One thing is you sort of have the lines follow each other around. You can't have two arrows colliding. If you actually write down that reaction, it'll turn out that it can't happen. You'll have something weird where charge isn't conserved or something like that. But anyway, so here we have an electron coming in, and a positron coming in, and we have our two gamma radiations coming in, or going out, sorry. So this is, you write this E plus E minus goes to gamma plus gamma. So here's how we sort of can tell that this reaction is possible. And Feynman, the guy who created all of these interesting diagrams, had a nice little expression which was anything that's not explicitly prohibited will happen. So unless there's some law of nature that this can't happen, if you can make a diagram for it, it will happen and you will find it in nature. And so this kind of reaction is found all the time in nature. In the same way, you can reverse these reactions. Keep in mind, if we had a photon coming in and a photon coming in, an electron coming out and an electron coming out, we could we have a way to generate matter and antimatter with photons. So this is what's called pair production. We produce just a pair of matter and antimatter by colliding two very high energy photons together. And so this is a sort of common property of reactions. You should always reverse them. All reactions are reversible. So if you can have two particles come in to form another particle, you can do it the exact same way going the opposite. Sometimes they might not happen with equal frequency, but they'll still happen. Now there are two different types of reactions. So here's one of probably the most intuitive reactions, right? We have, these things in general are called scattering. Even if they create particles, they're called scattering reactions. The other type of reaction is called decay. So decay reactions are when you have one particle that says, I don't want to be this particle anymore, I'm going to collapse to a less energetic particle. And normally what less energetic means is that it'll go to a lighter particle. So particles like the top and the bottom, and similarly the tau and the muon, you can sort of see that mass increases this way in each of these categories. These guys don't really want to be taus. This guy doesn't really want to be a top. And they'll decay to a lighter particle. So the tau can decay to a muon, the muon then decays to an electron, but then the electron says, I'm already in the least energetic state. I'm already just only 0.5 MeV. So why do I want to become anyway? Yes?
Does the mass loss when it collapses translate to energy release?
Yes, it does. I'll actually show a nice little diagram, sort of see where all this energy is going. And also how we first theorized that neutrinos exist. Because it turns out that when we looked at these reactions and these decay reactions, we found out that there's a little bit of energy missing, just a tiny little bit. And people were like, oh, what if there's this little particle that we couldn't detect that had this energy? So as we get to electron, though, we have no lighter particle to decay into. And you think about it, if you had an electron going to a muon, unless you had another particle coming in, the energy isn't conserved, right? You just have energy sort of popping out of nowhere. And that doesn't make very much sense, right? We think that, mass or energy or some combination of those two should be preserved. So we don't want this way to go, but this way can happen. Or sorry, we don't want this way to happen, but this way. So let's look at the tau decay, because the tau is a nice example, because it's very clean. Okay, so one thing to look at first is that this is a weak interaction, right? Decays are weak interactions. And the basic vertex for the weak interaction, people usually draw the boson, the Z boson, the W boson as a little diagonal line like this. This is a W or Z. The Z is uncharged, so it's usually Z0, and the W is either plus or minus. It carries a charge. And it carries a unit 1 charge. So it's kind of like an electron or a positron. And then what comes in is, so these guys are called leptons. So in general, what we'll do is we'll just draw an L for a generic lepton. It could be an electron, it could be a muon, it could be a tau. And what it does is it turns that lepton into its corresponding neutrino lepton. So this is a mu. So it'll turn an electron into electron neutrino. Okay? So this is our new little basic tinkering block. And we can reverse this, and we'll turn an electron neutrino into an electron in the same way, so you can reverse it. And similarly, you draw little arrows. So I feel like opposite. So let's think about what we want, how we want to make a tau decay now with these two basic building blocks. So we have a tau coming in, right? And we want it to be a decay, so we don't want anything else to come out. Okay, so this is a tau. Now we know we can have an electromagnetic interaction, right? We can have a photon exchange. But we saw with the photon processes that the same stuff that's sort of coming in is going out, or it's turning into a photon. But the thing is that, if an electron comes in, an electron has to be coming out, or it has to annihilate with a different particle, right? We had the example of the positron and electron annihilating. But we don't want to have an anti-tauon or anything like that. So we only want a tauon coming in. So that means we have to use a weak interaction. And the strong interaction just happens to not matter because that's in between quarks. And so we're going to have one of these vertices. Okay. So we have a tauon coming in, and we want to, get rid of the charge of the tauon and turn it into a tauon neutrino. So we write that, and so this guy here must be a W minus. We're sort of making sure that the same amount of charge coming in is coming out. So this was W plus, then there's a lot of charge that sort of went nowhere. And now this W has to end up as something. It turns out that these guys will decay really quickly into, a lepton and a neutrino. These things are really short-lived, so we might as well just draw in our resulting stuff. So we have to have some minus charge coming out. So we can draw an electron, for example. And then we have to have a neutrino. So this makes some amount of sense, perhaps. So we can now draw our little reaction here. So we have a tauon coming in, goes into a tauon neutrino, an electron, and it happens to be an anti-neutrino. But as far as our detectors care about, anti-neutrinos and neutrinos are more or less the same thing. So this works out fine. And this is sort of a nice example of a process which can happen the other way, but it would be extremely, extremely hard to do, because you have to have 3 particles all being in the same place at the same time. And so we can turn the wheel backwards, but just energetically speaking, it's not that possible. So we will only really see this happen this way. And so what we've had is reactions where we start tauon, going to an electron. Because we can't really detect these guys that well. Particularly early on, we weren't able to detect them because they go really, really fast and they don't have any sort of charge. So they just zip right by our detectors without us seeing them. So we thought, oh, well, this tau's really massive. It's going to something really less massive. Where did all that energy go? And the answer was, oh, maybe there's these other little particles. And it turns out once we were able to detect them, we saw, oh, yes, there they are. And they're still really hard to detect. Usually, if you have, the way we detect them is we have a big jar of argon or some other, what's called inert gas, something that doesn't react with itself. And we look for this reaction happening. A little neutrino coming in, and then just randomly seeing leptons coming out. Randomly seeing an electron show up. And an electron we can detect, right? Because it has charge. You can see a little current going once it pops into existence. That's how you can see it. Okay. Are there any questions so far on this stuff?
How is that a decay? Why is that considered a decay reaction?
Okay, so the decay is essentially if you only have, if you have one particle here, spontaneously going to a couple of particles.
Somehow, if the neutrino or like something that you get there, why is it going in? Why is there error parts in?
Oh, so I guess the proper way to draw this would be this way. Awesome. And so what this arrow means is it's still coming out, but but what it is it's an anti-particle, because if you see sort of arrows going against the time, it's an antiparticle. But if you see them going with the time, it's a particle. It's sort of a nice bookkeeping technique, because like the particles aren't really traveling like this. This isn't exactly what's happening if you look really closely and you can theoretically see the particles. But it's a nice way of keeping track of everything. And it's a nice sort of way to quickly visualize it. But the arrows just represent whether it's a particle or antiparticle. It doesn't represent actual particle trajectories. Are there any other questions so far? Okay. So you can actually draw some pretty weird diagrams like this. So let's go back to our basic electromagnetic example. So like the course that you cover this kind of stuff in, if you decide to go into physics, particularly theoretical physics, is something called quantum field theory. These are all things that are contained in quantum field theory. And if you take a first course in quantum field theory, it turns out you will spend the entire semester only looking at this force, only looking at the most basic example, because it turns out that this weak force and the strong force get pretty complicated pretty quickly. So usually for just educational reasons, I'll mostly just use this guy, because it's pretty clean, right? You quickly can just sort of see things popping in and out. The strong force and the weak force will do weird things in certain situations. So let's go back to our electron interaction, right? We have two electrons coming in and two electrons going out, right? So we had this diagram for it, right? So this is what we call the first order diagram. So with this diagram, you can compute various properties of this interaction. You can see how likely is this reaction going to happen if you have lots of electrons flying around. Okay? But we can draw something called a second order diagram. You can sort of picture the Tinker Toy, Lego way to do this thing. Sort of imagine if you cut this guy. We're just combining four of these little basic vertices together to form a nice bigger picture. Now this thing is the same reaction, right? But it's a different diagram. Okay, it's a different way of expressing the same thing, it sort of seems. But it turns out you can also compute a all of these sort of interaction rates with this diagram. It ends up being much rarer, right? So this is a much more complicated thing to happen. You wouldn't expect it to happen. But it does sometimes happen and has the same outcome. So what you do is you add this diagram with this diagram. Okay? These we can also create even higher order diagrams. You can go to a third order diagram. And let's see if I can draw this in a sensible way. This will be a little bit confusing. Okay, so sort of what you can see here is there's a vertex here, the photon going this way, a vertex here, the photon going this way. And there are two vertices here, with the photon going that way and the photon going that way. So we can sort of connect all the lines. Just have to draw a little loop. And this way is just how it's working. So sometimes you'll have, two electrons coming in, they interact, and then there'll be, another interaction here. It's called a self-interaction, because the photon's sort of popping off, but then coming back to the same electron. So that's why it's called self-interaction. And it keeps on going. And this is an even more complicated diagram, so it's like a third order. And you can keep on going, and you can keep on adding more and more little interactions. This is why people sort of say particle physics is really, really hard, and why people always talk about theoretical physics is really, really hard. Because you have to keep on sort of keeping track of each of these guys, and if you want a more and more accurate result, you have to keep on adding more and more little corrections, they're called. And you can sort of draw, and it turns out that for even second order, you can visualize other ways of making a second order diagram with a different way. So for example, here are all, I think, like first order diagrams. It's not quite this interaction, but you can see there's a lot of different ways of doing it. This is like two gluons becoming W bosons. So you see there's all these different possible ways of doing this interaction, and they will get really, really complicated. And this actually becomes one sort of reasons why people don't like the standard model. You go back to it, there's a nice little mathematical formulation of this model. Now people don't really like it because it doesn't seem very natural as to why we're looking at two particles interacting, why it suddenly becomes really, really complex so quickly. You think there should be a more elegant way of doing it. Physicists like elegance. Though it might not seem it, everybody wants to just come down to some basic little formula to use. And there's some even bigger sort of problems with it when we look at this. Because we can look at a different diagram. So let's have so we have this diagram here. So this will become much more elegantly written. Okay, so this just has a little loop. So we have a photon, it just turns into a pair. So this is like, it's suddenly creating a particle and an antiparticle, and then they're both annihilating and having the photon coming out. Okay, so this looks like a pretty strange diagram, right? A pretty strange interaction with that. And it turns out it is a pretty strange interaction mathematically, because when you compute out some of these values, it'll actually end up being infinity. Either that it's like infinitely likely to happen, or it's infinitely not likely to happen, or something in between, And this is not a very good answer, because you don't see this happening infinitely many times. So physicists have created various ways of making this not show up, this weird little infinity not show up. And mathematicians really don't like it, because it turns out that you're just like arbitrarily cutting off a sequence at a certain point. It's essentially what it sort of ends up being like. I don't know if people have seen sequences in series, but it ends up being something like 1 plus 1/2 plus 1/3 plus 1/4. And it turns out that if you do this plus 1/5 plus 1/6 plus 1/7, although at the end, these terms go closer and closer to 0. 1 over a billion is pretty tiny. But if you sum them all up, you'll actually end up getting infinity. So that's not very nice. And what scientists basically do is they just sort of say, oh, let's just cut it off here. And they have a sort of technical way of doing that, but it's not very nice because, well, it used to be infinity and now it's something easy. But why is it something easy now? Like, this point that you cut off seems arbitrary. So this is one of the big issues that people have with how this sort of theory is currently formulated.
So that's the interaction between particle and antiparticle?
This is like, I guess just between you can make it be, you can just like reverse this line. And that's between a particle and an antiparticle. Before it was between an electron and an electron, but that's between an electron. So you have an electron coming in here,
Yeah.
and you have an anti-electron coming in here, because it's the arrows going backwards. Oh, this loop here? So this loop here, this loop here is a particle and an antiparticle. Yeah. So you have, sort of at this point, you see it's like a particle, electron, electron, but over here you have an electron, or a positron, positron, yeah. So you can almost sort of view that as an electron and an electron pop out, and then they annihilate. An electron and a positron pop out, and they annihilate. So it's pretty strange, right? And it shouldn't seem natural or easy. So it turns out that for a given process, we can draw lots of different ways of doing it. So now we're going to chat a little bit about the Higgs boson, kind of one of the big things in the news. Have people heard about the Higgs? Just by show of hands. Okay, nice. So getting your hands. So it was proposed for familiar with it. It was a big discovery last summer that we found something called the Higgs boson, which people sort of showed as the missing key to this sort of standard model. That the issue is that if you look at the masses of particles, these two guys are really massive. These things are really heavy. It's the giga electron volt. Very big. In fact, like one of these particles is like as massive as about as massive as like a gold nucleus, a gold atom. So that's pretty heavy. Gold is, hundreds of these particles combined. And that seemed pretty strange. And then these guys had 0 mass. And so we had to sort of have something to break the symmetry. You would expect all these guys to have around the same mass, but they have all these masses that are off from each other. And the Higgs boson is sort of this aspect of breaking this symmetry. And it's what ends up giving these two guys mass. But how do we sort of go about detecting this particle? And there sort of come up with all these interactions the Higgs boson could have. It ends up sort of behaving similarly to the W to Z boson. And here's sort of a list of those interactions, very confusingly written. So they like to draw this, the Higgs boson here as a dash. So you have various ways that they can sort of emit. So over here, these all, the Higgs is decaying to photons, so 2 photons. But there's lots of weird things that happen in between, right? We sort of show here that you can always draw sort of complicated diagrams for the same reaction. It turns out by the same sort of logic, you can create ones where it turns into different quarks. If you turn into, an up anti-up quark or a charm anti-charm quark, or various combinations of electrons, or it could turn into a photon. And they sort of computed out all these guys, right? And they were able to, using these sorts of techniques, compute how likely it was to decay at any given mass. So the Higgs got different masses, the decay depends on the mass. They're able to draw this funny diagram here. So what this essentially says is, let's say the Higgs is 100 giga electron volts. Okay? What's it likely to decay into? So what we do is we smash lots of particles into each other and see what comes out. So this is a picture of sort of the CERN detector. Each of these little lines is a different particle we're tracing. We smash together lots of hydrogen atoms in the center here, and then we see what sort of comes out, what sprays out. And we can detect what these particles are. And it turns out that you can't really detect the Higgs. None of these particles are the Higgs. You can't point at something and say, here's the Higgs. But what you can say is, oh, okay, I see a certain amount of electrons popping up. And if I just ignore the Higgs, I expect to see a certain number, right? I expect to see 100 per collision event. But then suddenly I say, oh, well, I'm not finding 100, I'm finding 102. And you might say, oh, maybe that's just within the range of error. You know, maybe I had a couple extra hydrogen atoms coming in, or maybe something weird happened. There was like background electrons coming out. But then when you sort of do this event again and again and again, and see what keeps on coming up, and we try to control these things, and you're still getting 102, then you say, oh, maybe that those 2 extra electrons I'm getting per event is something significant. Maybe it's something new, and some interesting byproduct of the collision. So what they do is they say, well, what are these extra things we're getting at? And what do the models think that we'll get at? So here's what the model thinks we'll get at. We will think that we'll get, you know, if it's 100 giga electron volts, if the Higgs is 100 giga electron volts, we'll say, okay, we're not going to find many Z boson combinations. You know, we'll find a couple, you know, photons, extra photons coming out. You know, we'll see a lot of W and W bosons. We're going to see a lot of charm quarks. You know, we're going to see a lot of gluons, a lot of tauns, a whole lot of bottom and anti-bottom quarks. This is what we expect to see if they had 100 giga electron volts. And similarly, if you have 200, you won't exceed practically any gluons coming out, or charm, or tau, but you'll see a lot of WW, ZZ, and pretty much nothing else. So you say, what are these extra things that we see coming out? And it turns out that it's not like, you know, 102 versus 100. It turns out it's like 100.000001 versus 100. You know, so it's really, really a tiny incremental change. So they have to run it for a really long time. They have to smash lots of particles together to get enough data to say we're not significant. That's why they had CERN, the Large Hadron Collider, open for, I think it was like 4 or 5 years before they could not really say anything important. But before they could say, we think we found the Higgs. And it turns out that we found it around, I think, like 120 or 130, somewhere around here, sort of between the ranges. And one of the ways that this is kind of important, this diagram is kind of an important way of looking at things, is that there's only a certain energy range you can probe. If you're smashing particles together, you have to design the big collider, the big machine you're smashing them together with, to work in a certain energy range. So, you know, the Large Hadron Collider is meant to work in this certain range. But how do you know it's here and not, you know, all the way, you know, billions and billions of giga electron volts? How do you know it's not really tiny? What they've done is they've had other experiments in the past. Before the Large Hadron Collider, they had what was called a Large Lepton Collider. So they smashed together electrons. And they were able to say, you know, we're pretty sure it's not in this range. Then another experiment was able to say, oh, we're pretty sure it's not like for more than 200, because like we've had enough events that we can be pretty sure that that there's not that many W bosons being produced, so there's not that many Z bosons produced. And then when they built the Large Hadron Collider, they only looked really at this energy range, because this was the only one that was left, more or less. So any questions about sort of this process of how they found the Higgs? Does this make sense to people, more or less? Or some else? Okay. So one of the sort of aspects of how do we sort of make this picture at the end, or this picture here? Okay. We need to somehow detect the particles. And the main way that we detect particles is something called the photoelectric effect. What the photoelectric effect does let's say we have some material, right? Let's say we have a silicon plate. We have the silicon plate, if you look at a small enough level, right? It's like lots of these little atoms with electrons circulating around it. And now one of the big discoveries actually of Einstein, that Einstein started built the theory for, was if you had a photon coming in and hits the electron with enough energy, the electron will actually sort of jump out. It'll jump out of the material and become a free electron. And now if it doesn't do anything quickly enough, it'll sort of be reabsorbed into the atom. It'll sort of jump back down. But if you have a current going through, the current can pick up the electron. The current will pick up the electron, will join all its other fellow electrons in a big current, so a big flow of electrons. And then you have a detector at the end, which says, sort of counts the number of electrons and says, okay, well, we got an extra electron. I guess that must mean a photon colliding. And that's one of the sort of main ideas of what I call CCDs. An even more accurate guide, which I actually use in plasma physics, is these are called avalanche photodiodes. And the idea is that one photon hits this device, and then they have a sequence of steps where it actually will multiply that one photon to be thousands and thousands of electrons, rather than just one electron. And that way you can make really precise measurements. And they use these things also in particle physics. So this is how we sort of end up detecting these little photons coming out. Because in the end, everything has to be an electromagnetic signal, right? We only have our computers. Everything has to be turned into something our computers can read. Computers can't read gluons flying around, right? We don't have a little gluon pathway through our computers. We have circuitry. So everything has to end up becoming some sort of digital or analog signal through our computer. And that's what these little guys end up doing. Is there any question about detectors that are used? Okay. So, moving forward a little bit, let's take a much larger scale. Right now, we've been looking at the tiniest of tiny scales. Let's take a really quick gear shift to the largest of large scales. It's sort of an interesting thing that physics has been, for most of its existence, has been focused on things we can see, right? We look around, we see phenomena, we can do it. But only really in the past, 50 or so years have we been able to dive both the really tiny scales and the really huge scales. It was only in, I think, 1913 that Hubble discovered that the Milky Way wasn't the only galaxy. People used to see little cloudy nebulas, and they thought they were just little things inside our own galaxy. But then Hubble was able to tell, oh, they're actually really distant galaxies. That sort of was the birth of really modern cosmology, that we're not the only galaxy. And as we've been sort of going along and along, I don't know if people have been sort of keeping up with the Nobel Prizes, but just, I think it was 2 years ago, one was given out to Perlmutter and Schmidt and Rees for the discovery that the universe was actually accelerating its expansion. The universe is just like slowly blowing up essentially, and it's blowing up faster and faster and faster. So that was sort of the discovery of this dark energy. Well, that one happened in like 1996, 1998, and that ends up being 70% of all the matter that we can see in the entire universe. How we can detect indirectly, we can't actually see it because it's dark energy. And then there's also dark matter, which unlike dark energy, clumps together. And we can actually see the clumping. People aim their telescopes. So let's say we have a distant galaxy here. We're here, we're going to look at that. At the galaxy. We would expect to see this weird egg-like thing, I guess. That's what we see most galaxies as. But if there's another galaxy, sort of almost in the way, so it's like we can still kind of see that galaxy. What this other galaxy ends up doing is bending the light. One of the sort of interesting things about general relativity is that everything sort of follows curvature of space-time. And everything gets curved. So instead of seeing a nice little clean image like this, we see a really sort of skewed out image. And we see our little lensing galaxy here. We see that weird little skewedness. It's all bent out of shape. So, and we can then look at to see how much mass is this galaxy, and compare to how much we can see. We see all the stars burning. Stars are most of the mass of the galaxy. But then we see, oh, actually, there's about 5 times as much mass inside the galaxy than we actually see. So we call this mysterious stuff dark matter. And there's a lot of theories about what dark matter could be. And it turns out that, we were talking about the physics of neutrinos and stars. Stars are hydrogen and helium mostly, and those are made of quarks. There's interstellar gas, which is also free hydrogen, free helium, also explained by our physics as we know. There's the heavier elements, which are only 0.03%. So everything that we really interact with right now is only 0.03% of the universe. Everything that Earth is made of. I guess there's some hydrogen in there too, but the mass is mostly heavy elements. So, our physics for these three guys, for a total of, what is it, like 5% of the universe, is pretty well understood. We know that stuff down pretty well. But it turns out, there's actually another 95% that we don't understand, and our standard model of physics doesn't currently have an explanation for. For a while, some guys thought they had an explanation for dark energy. That's something called vacuum energy. Essentially, remember how I showed these little loop diagrams? Remember how I showed these little loop diagrams? There's an energy associated with this little loop. Okay? And this sort of is a little mysterious because we can never actually detect this energy directly. So people sort of thought that these little loops, what's called vacuum energy, was accounting for dark energy. This was a very popular theory for at least a little while until people did out the calculation. It turns out that, if you look at the energy of dark energy per cubic centimeter or whatever of the universe is, like 10 to the 89 or something like that. I'll go with the units up here are something electron voltage. And then the energy of this little guy was 10 to the minus 10 electron volts. So it's pretty far off. I don't know if people are familiar with scientific notation, but this is 1 followed by 89 zeros. And this is 0.0000001 zeros. So there's 10 to the 100 off. So this is pretty far off. This is a Google, essentially, off these two numbers. So the astronomers like this, they will directly detect it. The theorists inferred this number, but it doesn't seem like a pretty good theory if it's that far off. So dark energy is still not very well understood. And so now people are developing new theories to try and explain this kind of stuff. What was this class? What? Okay. So people have been finding new explanations for this kind of stuff. People have heard about string theory, for example. There's also sort of more weird theories. There's quantum gravity, which is sort of a way of what they call quantizing gravity, which might offer some insight into this kind of stuff. But so far, these sort of fields are really theoretical. People haven't been able to make predictions that we can test. And if you can't really test it, it's not really physics, right? Because physics is about experimenting, about finding out the truth. How can you find out the truth if all you have is a bunch of formulas? So people are still working really hard, and that's an active area to try and think, if string theory is true, what would that mean? And how can we actually design an experiment to test it? So are there any questions about anything I've chatted about so far today? Probably want to hear more about something. I know I went pretty fast. I was trying to encompass most of modern physics in about an hour.
Those diagrams, what exactly is it? Collision, or is it just a particle comes and then it spontaneously reacts?
So I talked about sort of what happens over here.
Yeah.
So this is sort of one of the reasons why you shouldn't view these diagrams too literally as particle trajectories. Because if you think about, let's just look at the one vertice by itself, okay? One single vertice. So you have electron coming in, electron coming out, okay? Let's look at this possible reaction, okay? Now, you might say, oh, okay, so we could expect an electron to just suddenly turn into a photon and another electron, okay? But it turns out that you can't actually do this, because if you look at just energy conservation or mass conservation, you you have an electron coming in, an electron coming out, right? So that's all the mass and all the energy that's in the entire system. So how can you also have a photon? If you do have the calculation, this photon has 0 energy, right? Because this has some energy, x. Out comes x. What's this photon's energy? Well, I guess it has to be 0. Another reason why these are kind of called virtual photons. So you can't actually have this react. This reaction doesn't make any sense because photons can't have 0 energy, right? They're moving at the speed of light always, you know. So how can you have this little particle of light have 0 energy? So you can't do them too literally that way. But you know what's happening at this vertex, you know, nothing really happens at the vertex. It's just the vertex isn't a real thing that way. But it just turns out that every single interaction we can draw this way, we can see in nature. And if we can't draw it this way, we don't see it in nature. So that means that it ends up being pretty useful. You sort of extrapolate and say, okay, well I guess if I create a diagram now, it must actually happen. And that's how people sort of paint these predictions. And we do have sort of what's called a finding calculus. You do on this diagram afterwards, if you actually want to compute out everything. And if you do that out, you'll get more or less the right answers for everything. So, we'll let it. Any other questions? I guess we're out of time, so people want to go, but I'll be up there afterwards if there's other questions.